Previous few lectures we have been dealing with the finite element method for transverse vibration of the rotor system. Today's lecture also will continue with the finite element method. In this particular lecture we will be incorporating two important aspects in the rotating machinery. One is the gyroscopic couple, and we will see that because of this even for very small rotor system the size of the matrices becomes large, and we need to solve the eigenvalue problem or force response using some kind of software like MATLAB. And apart from this, we will see how we can able to incorporate the bearing stiffness and damping into the finite element formulation of the shaft system. So, basically we will see that if rotor is mounted, if flexible rotor is mounted on fluid film bearing, how we can able to handle with the finite element method. And we will see that generally especially the fluid film bearings, they are speed dependent, and because of that we may find that the property of this stiffness and damping will change with the spin speed of the shaft. So, that also can be incorporated if the bearing properties are speed dependent. So, let us see what are things we will be covering. So, we will still continue with the transverse vibration with finite element method. Both free and forced vibration can be done with the procedure described here. Especially we will be incorporating the gyroscopic effect of thin disc. We will not be considering the shaft gyroscopic effect, only the gyroscopic effect of the thin disc will be considered, but whatever the property of the shaft we considered earlier, the distributed stiffness and mass, that will incorporate, but will not incorporate the gyroscopic effect of the shaft as it is, but only of the thin disc we will be considering. Then rotors, flexible rotors mounted on fluid film bearing, how we can able to analyze such system, we will try to see. In both cases, as I mentioned, and we know that gyroscopic couple changes with speed and fluid film bearing property also changes with speed. So, we can able to draw Campbell diagram, that is nothing but variation of the world frequency with the speed, and from there we can able to obtain the critical speed of the system. So, let us consider a simple rotor system. In this particular rotor system, there is a cantilever shaft with a thin disc at the free end. We will consider the gyroscopic couple of this thin disc, but the gyroscopic couple of this particular shaft we will not consider. As I mentioned earlier, we developed the finite element in the previous lecture for Euler-Bernoulli beam element, and that particular model, it does not take into account the gyroscopic couple of the shaft itself. For that we need to have a Timoshenko beam model that we have not considered here. So, we will consider the gyroscopic couple of this. Now, because of this obviously the motion in two planes will be coupled. So, we need to write the element in both the planes. So, let us say for simplicity we are considering, for illustration purpose, only single element we are considering, and this is the element 1 in zx plane, and this is the same element in other plane, that is yz plane, because mass will be there at node 2, this is a node 2, and at each node there are 2 degree of freedom. So, in this particular plane, which is horizontal plane, this linear displacement and angular displacement. Here also at node 2 similar linear and angular displacement. In vertical plane, that is yz plane, we will be having these two displacements which will be different as compared to the horizontal plane. So, V1, Phi x and here phi y is there. So basically in this we have 8 degree of freedom of the system, because 2 at each plane at one node position, but if we consider in both plane at one node we have 4 degree of freedom, for 2 node we have 8 degree of freedom. Now we can able to write the elemental equation. First we are considering one of the plane motion, and we are not considering the gyroscopic couple of the disk. Later on we will add this particular gyroscopic couple effect. So let us write the elemental equation in zx plane, which is horizontal plane, and this is the mass matrix. You can able to see the rigid disk which is there at node 2 will contribute not only in the mass but also in the ID. This m has been divided, m bar, because this is common. So if we multiply this, basically this will be m and ID, where m bar is this one which is coming from the shaft mass matrix. This is the stiffness matrix of the shaft. So here we can able to see the stacking of the vectors u2, phi y2, u1, phi y1, u2, phi y2. So this is the stacking in one of the plane. Now in the yz plane, similar equations we can able to write, that is also without gyroscopic effect, and in this also mass matrix is exactly same, only thing these variables got changed. Now here it is v1 phi x1, v2 phi x2. The mass and diametral mass moment of inertia of the disk will appear here also, because they will be there in the same element in this vertical plane motion also. This is the reaction of the shear force and bending moment. Now these two plane motion we can able to couple. So before coupling, let us see the gyroscopic effect, how we can able to add it. So earlier when we dealt with the gyroscopic effect of massless shaft and the thin disk, we use a dynamic approach, even we use quasi-static approach. After that we discussed the dynamic approach with the influence coefficient method. So in that particular case we developed the we developed the equation of motion of a simple single mass rotor system like this, in which the mass of the shaft we neglected, and so this was the equation of motion which we derived earlier. And in this is the mass matrix, this is the stiffness matrix, which in turn we can able to get in terms of influence coefficient matrix, that will be the inverse of the influence coefficient matrix, and this was the gyroscopic matrix. Now we will be using this particular gyroscopic matrix in the finite element formulation. So we are taking this separately, but we will see that the stacking of the displacement vectors are different here, two linear displacement and then angular displacement, but in finite element formulation we have one linear, then angular, then linear angular for node 1 and 2. So let us see that particular gyroscopic matrix in our finite element this field variable stacking. So in place of x we are using u, in place of y we are using v. So you can able to see that the previous equation of the gyroscopic matrix will be taking this form. So the change of this will take place because of the change of the order of this variables. Now this equation we can able to expand. So what I am doing now, I am writing this for a node 1 and node 2 both. So you can able to see same, these are for node 1 and these for node 2. So basically this particular 4 by 4 matrix has come here. And all the other terms are 0. So this particular matrix has directly come here, because these variables are corresponding to this variable. So, just we expanded this so that we can able to couple this gyroscopic matrix with our shaft elemental equations. So, with this now we are coupling both plane motion. So, this is the mass matrix for that. So, you can able to see earlier we developed for horizontal plane and vertical plane, but now we have clubbed them. So, in this first 4 is corresponding to the node 1. So, first 2 is for horizontal displacement, these are for the vertical displacement at node 1. Similarly, here for node 2 horizontal displacement, vertical displacement. So, accordingly the positions of this mass matrices which we developed earlier will change. Now, the similar thing will be there here. This is the gyroscopic matrix which we have taken from the dynamic approach, because now order of stacking is same as the finite element formulation. So, this directly we can plug in. This is the stiffness matrix. So, the 2 plane motion elemental equation we have now assembled it in this form. So, depending upon the order of these field variable, the relative positions of the stiffness matrix terms will change. There is no external force. These are the reaction. There is shear force and bending moment. Now, let us see the boundary conditions of the problem. So, we have 2 elements, one element, and this node 1 is fixed. So, all the displacements, linear and angular displacements will be 0 there. This is free end. So, we will be having shear force and bending moment at node 2 0. So, these boundary conditions we can able to apply here. So, we have all this shear force and bending moment at node 2 0, and displacements at node 1 are 0. So, these displacements are 0. Similarly, we can able to equate the velocity terms at node 1 is equal to 0. Even for mass matrix, we will be having these as 0. Now, you can able to see that we need to take, because in the right hand side only the last 4 rows are having 0 values. These are unknowns. So, we need to eliminate them from the final reduced form of the equation. So, basically we need to eliminate the first 4 columns and first 4 rows of each of this. So, all these will get cancelled. First row, first 4 equations we will eliminate from everywhere, from here also. So, basically all these we need to eliminate. Similarly, for mass matrix, this mass matrix and stiffness matrix are symmetric, only the gyroscopic matrix is skew symmetric. So, first 4 rows and column of these matrices are eliminated. The remaining one we will write it separately. So, this is the reduced form of the equation of motion after boundary conditions. So, you can able to see corresponding to node 2 only we have the field variable, corresponding to 1 have been eliminated. So, this is the reduced form of the mass matrix, gyroscopic matrix. Still it is skew symmetric, this is also symmetric, this is symmetric. So, basically the form of these matrices M eta double dot, that means this vector, minus omega gyroscopic matrix eta dot. So, single derivative with respect to time, and this is stiffness into eta is equal to 0. So, you can able to see this particular equation is having this form, in which now because of gyroscopic couple we have additional term which is coming here. This particular, when in the equation of motion we have the field variable first derivative term, then the eigenvalue problem which is there earlier will no longer be valid, and we need to convert this particular equation of motion in a standard eigenvalue problem, that is the state space form. So, let us see how this particular equation of motion in which velocity terms are also there, how we can able to convert into a standard eigenvalue problem. So, this is the state space form we will be converting. Basically, at present our equation of motion is in the that is second derivative with respect to time. In the state space form, we need to convert this equation into single derivative terms. So, obviously, the number of equations will get doubled, but derivative with respect to time will reduce by 1. So, let us see how we can able to do it. So, let us define the eta dot as v vector, and if we substitute this in the equation of motion, you can able to see this will be m v dot. So, we will be having m v vector v dot, because acceleration can be written as v dot minus omega g, this can be written as v because this is a velocity, plus k eta is equal to 0. Now, I can able to express this in terms of v. So, that means I need to put all these in the right hand side. So, that means this will be equal to, this will become negative, and this will not be there, and then I need to do the inverse of m throughout. So, I will get this expression. So, omega inverse of m into g into v minus m inverse into k and eta. Now, this equation and this equation is required equation of motion. Now, you can able to see this equation and this equation, now they are single derivative terms, but number of equations will get doubled because earlier whatever the size of the eta was there. So, now we have this is also eta dot. So, the number of equation got doubled here. These two equation we can able to club like this. So, basically this particular equation is some we have clubbed this. So, you can able to see h we are defined as eta vector and v vector. So, you can able to see that once we are stacking this two one over another, this will be h dot, that means velocity of these two. D will be this form. So, basically you can able to see this is a null vector, this is identity vector, and this is the term which is corresponding to this, this is corresponding to this one, and this gyroscopic term is corresponding to this one, because this is velocity term and this is eta term. So, that is in the second place. So, is coming this side and this one. So, basically if we expand this equation, we will get these two equations back. So, this is the standard eigenvalue problem. Now, we have and the solution of this we can able to assume as some amplitude and E lambda t, where lambda is a eigenvalue. So, if we substitute this, because only single derivative is there in the previous equation, we will get lambda h naught is equal to d h naught, which we can able to put we can bring in one side, take, and we can take the amplitude as common. So, basically this is the standard eigenvalue problem, where if we obtain the eigenvalue of D matrix, we will get the eigenvalues n number of eigenvalues. Basically, in this particular case, because we don't have damping in the system, so basically this particular eigenvalue should have real part plus imaginary part, and the real part is corresponding to damping and imaginary part is corresponding to natural frequency. Because there is no damping in the system, so we expect this real part will be 0, because this is corresponding to damping. Even we have velocity dot term in the equation of motion, but that is due to the gyroscopic couple, which is not a damping. So thus we will find that eigenvalue will be pure imaginary, and the magnitude of that particular term will be the natural frequency of the system. So and obviously we will get in a complex conjugate form, but they will be pure imaginary eigenvalues. In case when we don't have the gyroscopic couple, so we will find that we will get two pair of same complex eigenvalues. Their magnitudes will be same if we are not considering the gyroscopic couple. But if we consider the gyroscopic couple, what will happen among these two? One of the magnitude of the eigenvalue, that is the imaginary part, will be a reduced value, and another will be having some higher value. So one will be alpha plus, that is, let us say, higher value, alpha minus superscript is lesser value. So if this is the condition, so that will be alpha will be in between, but alpha plus will be more than this and this will be less than this. So basically what is happening when we are considering the gyroscopic effect, this natural frequency which is corresponding to two different planes, because once we are not considering the gyroscopic couple, these two plane motions are uncoupled. So we expect in two planes the natural frequency will be same, but once we have the gyroscopic couple, because now the two motions are coupled, so we will not be having the concept of the natural frequency in horizontal plane and vertical plane, but we will be getting a system natural frequency which will be basically splitting with respect to this. So we will be getting will be having the splitting phenomena of the natural frequency because of the gyroscopic effect, and one will be less than this, another will be more than that. The lesser one we call it backward fold, and the more one we call it as a forward fold. Now through a simple example, let us see this particular illustration, how we can able to obtain the eigenvalues, from there how we can able to get the natural frequency of the system. Even we will see the eigenvectors, what is the form of that, and how we can able to extract the eigen mode shapes from that. So basically we have taken the same cantilever shaft and with a disc, and various properties are given here. So even we have given all the property, mass, stiffness, and in this basically we need to obtain the Campbell diagram and obtain the critical speeds. So these are the property of the shaft, and initially we are taking a single element for illustration purpose, but we will be showing the results for more elements. So these are the property. So these we can able to calculate based on the data given. Now the elemental equation. So this is the elemental equation. Basically this is the directly we have taken the reduced form of the equation of motion of, because in the previous discussion we have already shown that how we can able to apply the boundary condition and how we can able to get the reduced form of the equation of motion. So this is directly we are using that particular expression in which we have already applied the boundary condition. So, corresponding to node 2 only we have the field variable 1 corresponding to 1 already eliminated because of the fixed and boundary condition. So, this is the reduced form of the equation of motion, which is of the form of m eta double dot minus omega g eta dot plus k matrix into eta is equal to 0. So, this is the final form of the matrix. Now, if we want the state space form of this, we can able to write like this, where D is this matrix. So, we need to multiply all these matrices to get the D matrix. Now, you can able to see the D matrix will be double the size of the K matrix. K matrix is 4 by 4. So, D matrix will be 8 into 8, and various the state vector variables are given like this, corresponding to node 2 only they are appearing. Now, this mass matrix, gyroscopic matrix, K matrix in the reduced form we earlier wrote it. So, this is the same one. So, basically we will be multiplying and will be, because the size will be bigger. So, I am not showing this, but these matrices we can able to substitute and we can generate the D matrix for which we can able to obtain the eigenvalue. If we are operating at 0 speed, that means gyroscopic couple will not be there, G matrix will be 0. In that case, the earlier standard eigenvalue problem itself will be valid, because gyroscopic term is not there, that eta dot term is not there. So, whatever the eigenvalue problem was there earlier, that is valid, and in that case this eigenvalue will be square of the natural frequency, but in the state space form that is equal to the natural frequency. So, now I am giving directly the natural frequencies. So, this is the variation of the world frequencies. We will be showing in the tabular form how this has been extracted. So, we can able to see this for a single element. So, we are getting here, we can able to see, as we are increasing the speed, slight splitting of the natural frequency is taking place. So, one is corresponding to the forward world, the lower one is corresponding to the backward world. This is more predominant splitting in the second this one. So, you can able to see this is the forward world. So, initially when 0 speed is there, there is no splitting, but as we are increasing the speed, the splitting is more. So, this is forward world, this is backward world. This particular line is the line, the speed is equal to the natural frequency. So, wherever this line will intersect this curves, they will be the critical speed. So, here we will be having critical speed corresponding to the forward world and backward world. Similarly, here we will be having corresponding to the backward world, but we found that for second there is no intersection. So, the second natural frequency is not feasible. This phenomena we already seen while discussing the gyroscopic couple, that this gyroscopic couple second forward critical speed is not feasible for the discrete system. But the same thing if we obtain for more number of element, because we can able to divide the shaft into more number of element, and we can able to get the natural frequencies more accurately. So, this lower one is corresponding to the first forward and backward world. This is second this is corresponding to the second one. In this particular case, as we have increased the number of elements, now because shaft modes are also coming into the picture. So, basically now the shaft is having consistent mass matrix. So, these even for the second mode now we are getting the intersections, but you can able to see that the third mode now it is more this curve is more steep, so unlikely this will intersect that particular mode. So this is, we expect more accurate because more number of elements we have chosen, and we can able to see these are corresponding to the 0 speed. So there this curve meet, but as we increase the speed, the splitting is more and more. So basically this is a Campbell diagram. So now let us try to summarize this. So critical speed, this is without gyroscopic couple, that means when speed is 0. For element 1 we got this, for element 20 we got quite close value, but for second there is a difference, but we expect this will be more accurate. For one element we could not able to get even third mode, but if we take more number of elements we can get the third mode critical speed also. This is with the gyroscopic effect for element 1 and element 20, number of element 20. So in this splitting was there, but you can able to see small splitting is there, and always this will enclose the value of this one, because you can see one is less than this, another is more than this. When we took one element, there was no intersection of the second forward as we have seen in the graph, only the backward second was present, and higher we are not getting because only one element was there. For more number of elements we are getting intersections, and you can able to see they are enclosing this particular values. So because splitting will take place around this. Similarly for this, this is the splitting. So one will be lower than this and another will be higher than this. This is the mode shape. So this is the amplitude of the mode shape, because eigenvector also will be getting as complex, but only real part or imaginary part will be there. If you take the amplitude and plot it with respect to the shaft length, this will be the for first mode, and this is for the second mode, and higher modes also we can able to plot it. And let us see the how eigenvalue generally we will get it. So this is for one element. So you can able to see that for one element, when we are considering the very low speed, that is omega nearly 0, so you can able to see the eigenvalues, 4 sets of eigenvalues are same. So these are complex conjugate, but another set is there having same value. So as we discussed, we will get 2 sets of similar eigenvalues, and they will be same magnitude. This is because the coupling between two planes are not present, but yeah. So this is for high speed. So for high speed we expect that now this eigenvalue, so this is one complex conjugate, this is another. So now they have different values, and you can able to see one is less as compared to the previous one, and another is more. So basically the splitting of the natural frequency is taking place. So we can able to see that it was 1927. Now one of the pair has a smaller value, another is a higher value. So as we discussed earlier, so we will get one is less, which will be higher than the without gyroscopic couple, and this will be higher and this will be lesser. So one is higher, this is higher, and lower one is this one. And if we see the eigenvector, so we will get because the reduced form of the eigenvector had this form, and the state space form of the eigenvalue had 8 by 8 size. That means we had stacking of this eigenvector as eta and eta dot. So the 8 values of the eigenvector, these are very small. Some of the values I have shown here, that is more important. So basically corresponding to one eigenvalue we will get 8 number of eigenvector for one element, So, and stacking will be first 4 will be this and next 4 will be velocity of these. So, now you can see that here first is the horizontal displacement and the third is the vertical displacement. First is horizontal displacement, third is vertical displacement. Now you can able to see because they have 90-degree phase difference. So, they are like this. So, basically if you multiply minus j with this, you will get this. This is because they are corresponding to two different planes. One is horizontal plane, vertical plane, they have 90-degree phase. So, we expect them to be 90-degree phase, and then eigenvector also. And another observation is we are getting the purely either imaginary quantity or real quantity, because there is no damping in the system. So, that is why we have this particular typical behavior of the eigenvector. But when we will consider the damping, especially like fluid film bearing, we will see that both quantity will be complex, and then plotting of the mode shape will be more difficult in that case. Now, we will take up another case in which we will be mounting a flexible rotor on fluid film bearing, and through one example directly we are explaining how the fluid film bearing elemental equation can be clubbed with the finite element equation of the shaft system. As we have done in the previous case, the gyroscopic couple matrix we developed separately and we clubbed with the finite element original shaft elements. So, likewise only we will be developing the equation of motion for the bearing separately, and then we will club with the elemental equation of the shaft. So, for this we are considering a simply supported shaft like this. This is a flexible shaft. In this particular case, we will be considering the Euler-Bernoulli beam model. So, basically we will be treating this as finite, we will be discretizing this onto one element for illustration, but we can able to increase the number of elements easily. These bearing are basically fluid film bearing, and they each of them are described by 4 stiffness and 4 damping terms. So, total 8 properties are there for each of the bearing. So, we have coupling of the motion in both the plane because of this particular fluid film bearing, and the property of these bearings are given here. So, let us say left hand side bearing is A. So, this is the property, and bearing B, this is the property. In the subsequent class, we will explain how we can able to get this property for a typical fluid film bearing, especially if we have some kind of approximation like short bearing approximation. So, this is the various other property of the shaft and material property of the shaft. So, for illustration we will show only one element, but that can be extended for high elements. So, now let us see how we can able to model this. So, we have taken one element. So, this is the shaft element in one of the plane, because now both plane motion are coupled. So, only one elements we have considered. So, similar to the gyroscopic couple case, we need to write the elemental equation for both of them, and then we can combine them in the two planes. So, now let us take the bearing model. So, earlier we know that the bearing fluid film forces in horizontal and vertical direction for one of the bearing we can able to express like this, where these are the property of the stiffness or damping and stiffness of the bearing. Now, this we can able to expand like this, because this is for at node 1. Bearings we are defining in terms of the linear displacements only. So, we are not considering the stiffness and damping because of the tilting of the disc or tilting of the shaft, only the linear motion we generally consider. So, if we introduce the tilting also, so corresponding terms will be 0. So, basically we expanded these equations in the 4 by 4 by introducing some variable. So, basically if we multiply these 4 equations, finally we will get this only. So, this is the expanded form of this for node 1. So, this is for bearing 1. On the same line for bearing 2 we can able to write, only thing with the bearing property, the superscript is representing the, so this is representing the bearing 2, is not the square, and if we expand this we will get similar to the previous one, only thing is here subscript 2 is coming and here field variables are corresponding to node 2 because these are attached to the node 2. These are the fluid field forces. Now, governing equation for the both the bearing. So, what we have done, we have combined the both bearing equation of motion. Now, you can able to see the stacking of the vector is for node 1 and node 2. So, basically for node 1 we have the first 4 this equation, and for node 2 this was the equation, and these two are the null matrices. Similarly, for stiffness the first 4 rows and columns are corresponding to bearing 1, which was multiplied by this, and the last 4 row and columns are corresponding to the node 2. These are the bearing forces at node 1 and 2. So, this is the equation of motion for bearing alone of both the bearing. Now, we can able to now this is the equation of motion for the shaft alone. So, you can able to see now we have clubbed the 2 plane motion as we did for the gyroscopic case. So, this is the mass matrix, this is the stiffness matrix, these are the reaction shear force and bending moment. So, this is the equation of motion of element of the shaft. Now, because both the equations are having similar stacking of the field variable, now we can combine them. So, basically this is the mass matrix as we had earlier, this is the bearing damping terms. So, you can able to see just we have added, because now order of these field variables are same as this one. So, we added this. Similarly, the stiffness of the shaft as well as of the bearing we have combined here. So, you can able to see the contribution of the bearing to the shaft element stiffness are these. So, these are the contribution from the bearing 2 and these are from bearing 1. So, basically now we could able to get, and these bearing forces will obviously cancel the shear force, because once we have at the end of the shaft, once we are joining the bearings, there will not be any net force there. Moment will be there, but net force will not be there. So, they will cancel each other. So, these terms will get cancelled to each other. Bearing force and the shaft reaction force, they will cancel each other. So, basically if you see this equation of motion is now basically of this form. Here, because this is a free end, so moment will also be 0 here. So, you can able to say these are also 0, because it cannot, the bearing cannot resist any moment. So, this moment will also be 0. So, this is the form of the equation of motion. So, now as compared to the previous case, earlier it was minus omega g was there for gyroscopic couple case. Now, in place of that c has come. So, the state space form formulation will be exactly same, only thing will be in this particular D matrix, that minus omega g will be replaced by C. So, this will become positive, omega will not be there, and C. So, C is now a damping matrix, it is not the gyroscopic matrix, and the eigenvalue now we expect to be complex, even eigenvector we expect to be complex in this particular case. So, the complex eigenvalue will be of this form, both real part and imaginary part will be there. Second will be corresponding to the natural world frequency. The real part will indicate the damping in the system and at a given speed, and it is associated with each world's frequency. So, because this damping will be corresponding to that particular natural world, and if bearing properties are changing with speed, so they will change with the speed both. So, for this present illustration, we have not taken the bearing property as speed dependent, we have taken those properties as constant. So, and from this real part we can able to define a logarithmic decrement like this, which contains both alpha and beta. So, and negative sign is there. So, that means if this is 0, more than 0 positive, then system will be stable, and if it is negative, then system will be unstable. So, in the subsequent lecture we will be seeing this stability aspect in more detail, but with the finite element formulation of the state space form, we can able to judge the stability of the system directly using the logarithmic decrement. Now, this is the natural frequency and logarithmic decrement which we have obtained. So, basically we have solved the D matrix, because we know the D matrix completely, mass, stiffness, damping matrix. We have obtained the eigenvalue and eigenvector of that, and using the imaginary part of that we got the natural world frequencies of the system, and from the real part and the imaginary part, by the definition of the logarithmic decrement, we could able to get this. Here we can able to see all are positive, that means system is stable for all the world frequencies, it is not unstable, but you can able to see that gradually those are decreasing. These dampings are very high, maybe because of whatever the bearing property was taken is because of that. So, but at higher speeds we are having lower logarithmic decrement. Now, just to compare how if in case of fluid film bearing, if we have simply supported end condition, like we consider the fluid film bearing, if it is simply supported end condition, so what will be the change in the natural frequency? So, you can able to see with fluid film bearing, basically the value of the natural frequency got decreased. So, this is just comparison of two boundary conditions. So, if we want to model the same system which is actually mounted on fluid film bearing by a simply supported condition, you can able to see how much difference will be there in the prediction of the world frequencies. In the previous shaft model using Euler-Bernoulli beam, we did not have the damping. So, let us see some simple damping model which we can able to consider. So, this is a proportional damping. So, in this particular case, earlier we had this elemental equation for mass, stiffness. Now, we want to add the damping also in the system. So, this we can able to, in the proportional damping, we can able to write the damping in the terms of mass and stiffness proportional to mass and stiffness, and there is some constants, and Rayleigh's damping factor, these n1 are defined like this. So, for a particular mode, let us say nth mode, this is the damping ratio, these are the constant, this is the natural frequency. So, if we are interested in certain frequency range, so we can pick up that two natural frequency which within which we want to analyze the system. So, let us say one is mth mode, another is the nth mode. If we write this for mth mode and nth mode, we will get two equations that can be written like this. Now you can able to see, we can able to get the A by inverting this matrix. So if we know the natural frequency of the system, two frequencies within which we want to operate our system, and damping ratio if we can able to obtain corresponding to that mode, then we can able to obtain the A0 and A1. So generally damping ratio we can able to get the through experiment with relatively easy as compared to the damping matrix itself. So once we get this, we can get the A0 and A1, and then our C matrix is defined. So this generally we use it if we want to introduce some kind of damping in the system to have more realistic analysis of a rotor system. So this particular damping is of the shaft damping itself, but is proportional to mass and stiffness. Today's lecture we first started with the gyroscopic couple of a disc, how we can able to incorporate in a finite element formulation. As such, we did not consider the gyroscopic couple in the shaft itself because we need to have a Timoshenko beam model for that, and till now we have only considered the Euler-Bernoulli beam model. So in that particular case, when we considered the gyroscopic couple of the disc, we saw that the two plane motions were coupled and the world frequency was dependent upon the speed, and for obtaining the critical speed of the system we need to obtain the Campbell diagram, and then we saw how we can able to incorporate the fluid film bearing model into the equation of motion of the rotor bearing system. In this particular case, we saw that coupling of the motion in the two plane, also the eigenvalue and eigenvector were more complex, especially the eigenvalue we have seen that it become complex, and not only we have the natural frequency information, but also damping, or in terms of the logarithmic decrement we can able to judge the system stability. And then we took one simple Rayleigh damping model, which generally we can able to use it if we want to introduce some damping into the shaft model, so that we can have more realistic analysis of the rotor system. Now with this we will be completing our analysis of the transverse vibration of the rotor bearing system. Now in the subsequent class we will study the instability in the rotor system, and we will see that various sources of instabilities are present in the system, and we will see in more detail of this in the next class.